Hello, 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 hello. Solutions to problem 90. Why are the rainbows very strongly linearly polarized? There are 5 talks on rainbows. All of those are on my YouTube channel. You may want to look at least at one of them. It is lecture 32 of 802. It is lecture 22 of 803. There is a playlist which I call 1 hour special talks. There is a talk which is called How to Make Teaching Come Alive. And I cover rainbows. There is a colloquium I gave in Delft, the Netherlands in 2011. On that playlist you will find that talk. And I showed rainbows and I talked about rainbows. And then there is a playlist which is called 1 hour talks for NHK TV Japan. Those lectures were all shown on TV in Japan. And one of those covers in detail rainbows. In all these lectures do I thoroughly go over the geometry of the rainbow. The light that refracts into the water drops, reflects at the back of the water drop, and then refracts back into the air. So refraction, reflection, refraction. In all of them, I do a demonstration. I create a fake rainbow. I call it a fake because I only use 1 water drop. However, as I explain in those lectures, the rainbow that I produce, the fake rainbow, has all the features of the real rainbow. And that includes the fact that the rainbows are strongly linearly polarized. I demonstrate that. The one I create in lecture hall only shows you the primary bow because the secondary bow is just too faint. So let's concentrate on the primary bow. In all 5 lectures do I mention that the bow is very strongly linearly polarized in the direction tangentially to the arc, which is part of a circle. In only 1 lecture do I explain why that is the case. And for that you will have to watch lecture number 18 in 803, where I discuss what is called the Brewster Angle. After this short introduction, let's take a look at some key pictures that are chosen from these lectures. Okay? If you're ready, then I'm ready. So here you see a picture of one of those lectures, one of those 5 lectures. I don't remember which one. I create a fake rainbow projected on a white screen. And I do that with one water drop. But I have argued with you why that fake rainbow that you see here, where red is on the outside and blue is on the inside, why that rainbow has all the features of the real rainbow. Therefore, it should also be very closely to 100%, not quite, but very strongly linearly polarized in the tangential direction. And so I hold up in front of this screen for all students to see, I hold up a large sheet of polarized light, polarizer, a large sheet of polarizer, which has the direction of polarization in this direction. And so you see, you kill the light from the rainbow, which indicates that the light of the rainbow is strongly polarized in this direction. You see that in all 4 lectures. Here you see lecture number 22 of 803. This picture you will see in all 5 lectures. I chose lecture 22 of 803. Light enters the raindrops, this I chose only one raindrop, at an angle of incidence I, is then refracted into the water, and I and R obey Snell's law. Then at the back of the raindrop, the light refracts, well, part of it refracts, some of it goes out. Of course, also here, part of it goes in and part of it refracts. So it refracts into the raindrop, then it reflects in the back, part of it, and then some of that comes out again here, so it refracts back into the air. I call this angle I, this angle R. So this angle R must be this angle R, and this angle R must be this angle R, and this angle R must be this angle R. The light that I then see, when I look up to the water drop, I'm way down there here, the light that comes from this angle phi. So it enters, reflects, but my eye will see only this light from this angle phi. In all 5 lectures, do I calculate for you I pick a random I, and I change I, of course. Then I calculate R, and then I calculate phi. That is simple geometry. And you can check one of those lectures to follow that geometry. And so you here see the result. I think this is again lecture 22 of 803. So you see I going up steps of 10 degrees. Then R goes up, which is what you expect, Snell's law. But what you do not expect, that phi reaches a maximum. And for larger angles of I, phi goes down. And it is at this value, very close to this value, where the rainbows occur. And that I do explain in all 5 lectures why it's there. I show you this for the following reason. R, when the primary rainbow is formed, is very close to 40.4 degrees. And that is key in understanding why the bow is nearly 100% polarized. So hold on to the 40.4 degrees, and I will now introduce you to what we call the Brewster angle, which I explain in great detail in lecture 18 of 803. This angle happens to be very close to the Brewster angle in going from water to air. Reflection inside the water drop. So if you're ready for that, we'll go back to the hall, where you will see some information about the Brewster angle. All right, so now we will finish the solutions by discussing the Brewster angle, which I cover in great detail in lecture 18 of 803. It's a difficult lecture. You may not even want to attempt to follow it. It discusses the so-called 4 Fresnel equations, which tell you everything you want to know about when light reflects and refracts, going from one medium to another, or reflects. Not an easy lecture. I do truly stunning demonstrations. It's worth watching that lecture for that reason. Take a look. Medium 1, index of refraction N1. Medium 2, index of refraction N2. Light comes in at an angle of incidence theta 1, refracts into medium 2, and this angle is theta 2, and they are connected to the sine of N1, the sine of theta 1 times N1, if the sine of theta 2 times N2. Snell's law. When it refracts here, these two angles are the same. I now derive in lecture 18, again it's not simple, that when the tangent of this theta, of this angle theta, is N2 over N1, that the reflected light is 100% linearly polarized. And we call that angle then the Brewster angle. I do some stunning demonstrations where light goes from air, so this is air, to glass. This is air, this is glass. Index of refraction N2 would be 1.5. Air would be 1. And when the light refracts off glass at that angle 56.3 degrees, which is the Brewster angle, then the refracted light off glass is 100% linearly polarized. And I show that, I demonstrate that in lecture 18. At time 50 minutes and 41 seconds into the lecture, I come to this conclusion, which is the result of one of those Fresnel equations. Non-intuitive, but true. So now, let's go back to the water drops. The light refracts on the back of the water drop. When the light is in the water, it refracts off air. Outside the water drop is air. So N1 is then the index of refraction of water, which for visible light is very close to 1.33. And of course N2, which would be the air, this is water, this is air, would be 1. So N2 divided by N1 would be 0.75, and so the Brewster angle, which would be this angle then, 36.9 degrees. And go back now to my earlier video. That angle R as in Richard, which is the angle of incidence when the light refracts off the back of the water drop, that angle R, when the rainbow occurs, is very close to 40.4 degrees. And look how close the 44 degrees is to the 36.9. And that is why the light is almost 100% polarized. It's very strongly polarized. It's also true for the secondary bow, but I didn't discuss that in any detail, because what counts here is the principle. But you can go over the exercise for yourself to see how close the reflection is when we deal with the second rainbow, how close that is again to the Brewster angle, which is 36.9 degrees. The demonstrations that I do in lecture 18 are many. I don't do the rainbow there, but I show you some remarkable demonstrations that you can even do at home by reflecting light off glass. For instance, glass that you have in front of maybe your portrait. So I do suggest you look at 18, lecture 18, and get the best out of it. The best may be the demonstrations, but at least I want you to see that the Brewster angle can be derived from first principles, from Maxwell's equations. So remember, when you drive your car on the street, the sun is in the sky there, and there is water on the street. And that sunlight reflects, and that blinds you. However, if the angle is just right, or close to right, that radiation is 100% linearly polarized in this direction. Therefore, you wear polarized sunglasses which are polarized in this direction to kill that reflection. So in that case, it is the reflection from light that is in air and reflects off water. Calculate for yourself what the Brewster angle would be. So N2 would then be 1.33 and N1 would then be 1. So now you understand why people like to wear polarized sunglasses. And the classic question of many of my exams is, in which direction are your glasses polarized? Always in this direction, to kill the polarized radiation from the reflection. There was a lot of physics and it wasn't easy, but who says that physics is easy? However, and this I mean from the bottom of my heart, physics is there to make very difficult things easy. Because imagine without physics how you could ever even approach this problem. You would have no clue. But it is through physics that you can see through it and come to an understanding. Physics broadens your horizons. and they have broadened my horizons, and they have enriched my horizons. I was born for physics, I think. Have a nice day, take care, and surely we will be friends. That's never an issue. We don't need any physics for that, do we?